Okay, this is lesson 6.5, graphing reciprocal trig functions. In a previous lesson, we looked at graphing the primary trig functions, and we can graph the reciprocal functions by using a process similar to the one we did in the rational unit when we graphed reciprocals of polynomial functions, like where we took the graph of a line and graphed its reciprocal using key properties, and when we took a parabola and graphed the reciprocal of a quadratic by taking some key properties. We can do the exact same thing with the primary trig functions. It's just matching up what primary trig function and which reciprocal are related, and then using those exact same properties we did in the first couple lessons of the rational functions unit. So first we'll review which reciprocal trig functions are reciprocals of which primary trig function. We'll review also evaluating, how we could evaluate in our calculator the reciprocal trig functions at certain angles and radians. And finally, we will review the properties of reciprocal functions and then sketch one of the reciprocals. And then I'll ask you to sketch the other two. So first things first, which functions are reciprocals of each other? Cosecant is the reciprocal of sine. So cosecant is just simply 1 over sine x. Secant is the reciprocal of cosine, so it's just 1 over cosine x. And cotan is the reciprocal of tan, so it's just 1 over tan. So if we're given one of those reciprocal ratios and asked to evaluate, we can do so by using its related primary function. For example, if we want to evaluate cotan at 2.27, that would be the exact same thing as evaluating its reciprocal tan at 2.27 and taking its reciprocal, or doing 1 over tan of 2.27. And if our calculator is in radians, we can evaluate it directly. My calculator is not in radians, so I'm going to change it. And that's not how we change it. I forget how to change this one. Let's see, shift mode, there we are, 4 radians. Perfect. Now I'm in radians, and if I want to evaluate cotan 2.27, I would do 1 divided by tan 2.27. And I would get negative 0.841. And that's how we can evaluate. Try it in your calculator to evaluate cosecant of negative 3.66. And to do so, we would take its related function. Cosecant's related to sine, so we'd be doing the reciprocal of sine, negative 3.66. And we should be able to get an approximate answer of 2.02. So try that one in your calculator to see if you can come up with that answer. All right, properties of reciprocal functions. I've gone ahead and pre-written these out, and I'll give you a chance to write them out as I kind of talk about each one as we go through them. The first one is that when the original function and the reciprocal function will share a point when y is 1 and when y is negative 1. So wherever the original function equals 1, the reciprocal function will also equal 1 at that point. And that's because the reciprocal of 1 is 1. Same with negative 1. The reciprocal of negative 1 is negative 1. So that will be a shared point too. So at those y values, 1 and negative 1, whichever x value the original function has that produces that value of 1 or negative 1, the reciprocal will also be 1 at those spots. So we'll review that when we graph again. Next is about where it's positive, where it's negative, where it's increasing, where it's decreasing. When the original function is increasing, the reciprocal should be decreasing. Like when the original function's y values are numbers like 1, 2, and 4, the reciprocals of those numbers would be 1, 1/2, and 1/4. 1, 2, 4 is increasing, but 1, 1/2, 1/4 is decreasing. So there's a relationship there, and vice versa. When f of x is decreasing, the reciprocal should be increasing. When the original function is positive, the reciprocal should also be positive, and that's because the reciprocal of a positive number is still positive. And when the original function is negative, the reciprocal should also be negative, and that's because the reciprocal of a negative number is still a negative number. Like the reciprocal of negative 5 would be negative 1 over 5. Still negative. Next property, this one's pretty important. When the original function equals 0, the reciprocal will be undefined. So we'll have vertical asymptotes wherever the original function equals 0. So wherever it crosses the x-axis, we're going to draw a vertical asymptote for our reciprocal function. And finally, if you have a local minimum or a local maximum or an absolute minimum or an absolute maximum on a graph of an original function, it's going to become the opposite for the reciprocal. So for example, a local min for original function will become a local max for a reciprocal. A local maximum will become a local minimum. An absolute maximum will become a local minimum. Potentially an absolute minimum, but at least in that domain it will be a minimum. So minimums become maximums, maximums become minimums in that little area of the graph wherever the graph exists. And vice versa. Oh no, vice versa, I already kind of said that. So let's try to use these properties to graph a reciprocal. And we're going to do cosecant. So we're going to start by, I'll try to keep the properties on there. We're going to start by graphing sine, and then we'll graph its reciprocal using those properties. So we need to remember the key features of sine, and I'm going to use my scale as if that's a half. So this would be 1, and this would be negative 1. So sine starts at 0, 0. And after pi over 2, it goes to 1, a maximum. At pi, it's 0. At 3 pi over 2, it's at its minimum, negative 1. And at 2 pi, it goes back to its resting spot at 0. So if I were to connect that, it would look like this. And there is our sine curve. If we wanted to graph it over a second cycle, we would just continue the pattern backwards. We went up here, so we're on our way down. So we go down, 0, max, 0. So we can continue this graph backwards, go through, hit a max, come back down. So there's our sine. All right, and let's look for our properties. Let's start by plotting our asymptotes. Asymptotes are going to occur wherever our original function equals 0. So for cosecant, our original function is sine. The reciprocal is cosecant. So where sine is 0, well, sine's 0 at negative 2 pi. So we've got a vertical asymptote there. Sine's also 0 at negative pi. So we've got an asymptote there. At 0 at 0. So we've got an asymptote there. It's 0 at pi, so we've got an asymptote there. And it's 0 at 2 pi, so we've got our last asymptote on this graph there. Lots of asymptotes. There's an asymptote every pi, basically, in either direction and any direction. So there's our asymptotes. The next place would be a good place to look would be we have shared points at 1 and negative 1. So that means this point is shared between the original and the reciprocal. This point is shared between the original and the reciprocal. This point shared between the original and the reciprocal, and this point shared within the original and the reciprocal. All right, that doesn't really help us. Well, I mean, it kind of helps us, but it doesn't help us get the shape of what this function is going to look like. So let's move to the positive-negative property. When the original function is positive, the reciprocal will be positive. So that means between these two asymptotes, the original function is positive everywhere that it's not 0. So that means our reciprocal is also going to be in this section of the graph only. It's not going to go down here. In this section, we have a negative piece. So that means the reciprocal is going to be negative. So that means it's only going to exist in this section and not be up here. See where I'm going with this? The reciprocal will be in this section and in this section. So we have shared parts to our graph. So the parts that are empty on the original will still be empty when we graph our reciprocal. Local mins will become local maxes, and local maxes will become local mins. This is a local maximum. Right here, it's a maximum point in this section of the graph. So that means it's going to become a minimum point for our graph. So our graph is going to exist above that point and including that point. So it's going to be up here. Just like when we have a local minimum here, it's going to become a local maximum, so our graph's going to bend down and approach our asymptotes. So we have a section of graph here, and continuing we have one here and one here. All right, still doesn't really help us. Well, get a shape. The last one that's really going to help us get our shape is this increasing decreasing property. When f of x is increasing, our reciprocal should be decreasing. So if we're increasing in a curved shape right here to a local max, our original should be decreasing. So from here, approaching our asymptote, we should be decreasing in the similar shape, curve, to a local minimum, since the original was a maximum. So our function is going to look like this for this section. And our original is decreasing here, so that means our reciprocal should be increasing. And that's how we start to get our shape. So I'm going to highlight that piece. This is part of our reciprocal. And we have similar shapes in each of the sections. They look like little mini parabolas in each section of the graph. So here we were decreasing, so that means our function is going to be increasing, and we bend to approach asymptotes. Here we're increasing, so our function is going to be decreasing. And there we have another piece. In this section of the graph, our original is increasing, so our reciprocal decreasing. Our original decreasing, our reciprocal increasing. And always bending to approach our vertical asymptotes. That's what asymptotes do. They're like magnets for functions. They pull the function towards them. And our last piece, decreasing on the original, increasing on the reciprocal, approaching that asymptote. And then our original is increasing, reciprocal, decreasing. And there we have 2 cycles of cosecant. Where are our vertical asymptotes? We have lots. On what's graphed here, we can list our vertical asymptotes in a few spots. We have a vertical asymptote at negative 2 pi, negative pi, 0, pi, 2 pi. What's a period? Well, a period is one cycle. The period of an original and the reciprocal should be the same. So we have a up curve and a down curve. And to go up, vertical asymptote, down, vertical asymptote, that takes 2 pi. Your period of your reciprocal is 2 pi, the same as the original. Domain? Well, our domain, this function exists everywhere with the exception, of where the vertical asymptotes are. So, for what we have graphed here, we can say that our domain is that x belongs to real such that x does not equal, and we'll list our vertical asymptotes. Negative 2 pi, negative pi, 0, pi, 2 pi. And there is series notation to write a little mini equation for where each vertical asymptote is, but for our purposes, for this graph, since we only graphed it on 2 cycles, we'll just write our domain for the 2 cycles. And we can do the same for our range. Range is a little tricky here. Our function, let's call it y, because y equals cosecant x, so we'll call it y. Y belongs to real such that here we have a gap in our range. Our function exists here, and then doesn't exist in the middle, and then exists down here. So that means our function needs to be greater than 1 or less than negative 1. And one way that you can express broken parts of a line, that seems confusing. If you were to put all these numbers on a number line, like negative 3, 4, 5, 6, 7, 8, 9, what am I doing? 5, 4, 3, 2, 1, and then have a break from 1, 0, negative 1, and then continue negative 1, negative 2, negative 3, negative 4. When you have 2 separate sections on a number line in which the sections are separated around the same number, 1 and negative 1, by same number I mean the absolute value of the same number, you can use the absolute value notation to designate that range. So in this case, the absolute value of y needs to be greater than or equal to 1. And that would take care of this branch for when it's positive, 1, 2, 3, 4, 5. And when it's negative, negative 1, negative 2, negative 3, negative 4, the absolute value of those would be 1, 2, 3, 4. So that would fit the criteria for both of them. So you can use absolute value notation to show the two separate pieces. And that's it for your range. When you're graphing the reciprocal of cos and the reciprocal of tan, throw them into Desmos and see if you've graphed them correctly, or alternatively, check the solutions on the course website. So try graphing secant and cotan, and good luck.